Okay, I understood three the most. It's a distillation column, and we're trying to control the distillate composition Y despite disturbances in the feed flow rate, which is F. F can only be measured, not controlled, and we know Y's measurements. So the first doing feedback, we're going to measure Y to manipulate R and B in order to control Y. Manipulated variables are the flow rates, and the control variables are the mole fractions. So we can use a composition analyzer to look at what Y is, and then from there use a composition controller to control both B and R in order to control Y itself. Um, for the feed forward design, we can preemptively measure F to manipulate R and B in order to control Y. So we can look at the flow composition, the feed composition with the analyzer, and then from there use a composition controller to control B and R in order to control Y indirectly. Seven was probably the one that I understood the least. Let's see if I can pull it up again. Okay. That we're looking at in irreversible consecutive reactions from A to B to C in a jacketed stir tank reactor. They give us four assumptions that we can follow. The contents of the tank and the cooling jacket are well mixed, and those volumes are also constant. They give us the reaction rates, R1 and R2. And this one I had a hard time understanding. I think that this means that you can ignore the heat that's stored in the wall between like the jacket and the reactor itself, I think. We can also assume there are constant physical properties and the heat transfer coefficients. So using that, we can look at the composition balances of A, B, and C, and we're assuming that A and B are both in the feed and like what is it, the product, but C is only in the product. It's not in the feed whatsoever. So from there, just looking at A to start with, we can do dCA dt. Um, I didn't show this, but the V was also in here, but since volume is constant, you can factor it out and you can divide it through. So you have Q initial times V C A initial divided by volume. And you can subtract that by QCA divided by V, and you subtract that by the rate reaction of the first from A to B. You can do the same thing for B, um, and for C as well, except for C, there's only the product you're looking at, not the feed as well. And then from there, you can do the energy balance for the reactor itself. Since volume, density, and heat capacity are constant, you can pull that out of this and you can divide it through, which I did down here. But you end up getting dt equals Q divided by V times Ti minus T. And that's subtracted by delta H1. And this is the first rate reaction divided by rho C from there you divide it through. You subtract that by delta H2, and this is the second rate reaction, also divided by rho C. And then you have adding the internal energy times the area divided by rho VC times the temperature of the coolant minus the end temperature. And then you can also do the energy balance for the coolant itself, V of C being the volume of the coolant in the jacket. And it's this, yeah. You can also do the same thing here. Like I pulled it out since those are constant. I didn't divide it through because it looked ugly when I did it up there. But you can. I forgot what those numbers were. I think those are the what numbers the first two problems were. Please let me stop. Okay. Yay.